Okay. I was finishing up my summary of the laws of electricity and magnetism that we've learned. And of course, the first one was Coulomb's law, and that was just the forces between stationary charges. And we know that much earlier than Coulomb, Dufay had discovered that electric charge comes in two varieties. And so if the charges are opposite, they will attract. If they're the same kind of charge, they'll repel. And the force just is like the force of gravity. It falls off like as the inverse square of the distance. Then Ampere's law we covered, which is a law that describes the forces when the charges start moving. And Oersted and Ampere discovered that currents cause magnetic fields, and those magnetic fields exert forces on other moving charges. Now, Faraday's law, I said at the end this morning, the image that should come to your mind when you think about what Faraday discovered is this wire loop and the magnet going through it. And when that magnetic field through that loop changes, it creates a current in the loop that opposes that change. Now, so now what's the law that describes this? Well, what I told you before was the rate of the change of the magnetic flux through the loop is proportional to the current. You remember that? So the way we can write that, if we do that in an equation, I think I've used this little delta sign as a change in something before. Do you remember that? So if the magnetic flux through the loop, the change in the magnetic flux per time interval. Okay, so this is like the rate that the flux is changing. Because the change in the flux given a certain change in the time. Yes? Oh, yeah, sure. Remember that magnetic flux we defined as the magnetic field through the loop, okay, multiplied by the area of the loop. Okay, so remember that there were different ways to change the flux. The field strength could stay the same if you could change the size of the area. Okay, that would create a change in the flux, right? So, one way that we talked about doing that was, let's say the magnetic field is in this direction. Okay, and I've got it's going right through my loop. Well, if I rotate my loop, okay, that you lose the amount of area that that is actually facing the magnetic field. Okay, so that's one way to change the flux. In addition to the other way, of course, being to change the strength of the field itself. Okay, so, but either way creates a change in flux, which then creates a current. Ben?
What's BA?
Oh, B, remember, is magnetic field. So this is just say something. If the magnetic field is coming from a magnet, then it would just be a number that associated with the strength of that magnet. How strong the field is from that magnet. And then A is the area of the loop. Okay. Now, So I told you that this is this was proportional to the current that's created in the loop, the change in the rate of change of the magnetic flux. Now, I'll go ahead and make this into an equation this time and tell you what else it depends on. So we know that the first term over on this side of the equation is the current. That's what I told you about before. So if you if you double the rate of change of the flux, say, you're going to double the current that it causes. But the other thing it depends on is, well, let me see if I can get you to guess. Let's say I take I have a nice thick wire, copper wire, for my loop. Okay, now we know, I told you before, copper conducts electricity really well, right? So it flows really easily through copper. Let's say instead of taking a nice thick copper wire, I take a skinny iron wire instead. Now, will I get the same amount of current? No, right? The skinny iron wire is going to have less current. Now, what's changed? Yes.
Both your material and your size.
Right, and the way that physicists describe the quantity here that is relevant is the resistance. Okay, if an electrical engineer will say, well, the skinny iron wire has a lot more resistance than the fat copper wire. So that's the other relevant quantity here that comes in on this side of this relationship. So it's the resistance of the loop, which actually is usually called R, but there's a case where people use the same symbol to designate two different things. We've been using R for distance, right? So if you ever see R in an electrical equation, though, be tipped off that it could be resistance, and you just have to judge based on your knowledge of the physics whether it's distance or resistance. Okay. So this is Faraday's law. Now, always, though, when you look at an equation, remember, in order to make any sense of this equation, you need to have all the words that go with it. You need to know how to interpret all these things. The symbols themselves don't mean anything unless you really know the physics and know how to interpret it. What's going on here physically that this equation describes is you have some loop of wire and you're changing the magnetic flux through it in one way or the other by moving the loop or by actually moving the magnet with respect to the loop. You're changing that magnetic field that's going through the loop, and that's causing this circular current that will create its own magnetic field to oppose the change you're trying to make. Okay, so that's what that describes. Now I have a question for you. What if I take the loop away? Let's say we don't have a loop. And that's right, we just have a magnet. Okay. We've got a magnet. And let's say we're moving it toward the right here. Now, consider now we don't have a wire, but just consider an imaginary loop there in space. We're going to move that magnet through it. Now, what's going on in that space? Whether we have a wire there or not, is something going on there? Ben?
There should be because, yeah, there should be.
There should be. I mean, yeah, there is. You know that if we had a wire there, the electric charges in the wire would start moving, right? So something's going on in this space, because we know if we put a wire there, the charges will start moving. Yeah.
Is it that if you had a wire there and then you removed it, then the electrical current would stay?
Well, I mean, you have to have charges there in order to get an electrical current. Now, for instance, but you can't ask this question. What if we don't have a wire loop, but what if we just put a charge? Say one electric charge in one particular spot where the loop was. Now, as we move our magnet, what's going to happen to that charge? Yeah, Ben.
It'll start moving around.
Yeah, it's going to start moving around in a circle. Now, in fact, all you have to do to know which way it moves is figure out which way the current would move around the loop, right? So it's going to oppose this magnetic field change. So it's going to spin around counterclockwise, at least from my direction. So where I've drawn the charge at the top of the loop, it would actually be going into the board here. Okay, now, so obviously there is a force on that charge. Okay? Now it's just a stationary charge that I put there. But as soon as I start moving the magnet, there's a force on it that's pushing a stationary charge. Now, yeah?
Is the charge like, is it just a piece of metal that's stationary?
Yeah, it could be. I mean, it could be, I mean, let's say, remember that when Coulomb did his experiments on stationary electric charges, he used these little things he called pith balls and charged them up just by touching things to them. Okay, so I mean that's what we could have there. We could have like a little pith ball that had been charged up with an electric generator. But it will start, if it's free to move, it will start moving as soon as you move this magnet. Now, if a stationary charge suddenly has a force on it, that means there's got to be an electric field. Nick?
If you put the magnet there, will the charge move around and stop, or does the magnetic flux have to keep changing?
Yeah, it has to keep changing. See, that's I mean, remember that this whole Faraday effect that we're talking about depends on the magnetic flux changing. It can't just be there. So you have to be moving the magnet in order for this to happen. But when you think of it this way, and you think about the effects on a stationary charge that you just put there, and you realize that the stationary charge will start moving in that circle if you move the magnet through what used to be the wire loop that I'm now saying we just have a stationary charge. You realize that, I mean, what's the kind of field that acts on a stationary charge? It's an electric field. So what's going on here is that a changing magnetic field causes an electrical field. So that's worth writing down. changing magnetic field causes a, let's call it circulating electric field. Which in fact is what causes the current to start moving in the wire loop when you have the wire loop there. Now, this should remind you a little bit of what Oersted and Ampere discovered. Remember, if you have a current, instead of a moving magnet here, if you have a current, an electric current, what happened? That set up well, let me draw that slightly better. That's supposed to be a side view of a loop. That set up a circular magnetic field, right? Circular B field around the wire. Troy.
If you actually put an iron loop there, would it become at all magnetized or not?
Oh, yeah, it would. Yeah. Just like if you put an iron loop here, charge will go through it, and you'll get a current. So there is this parallel between them now that we can see, that this changing magnetic field causes a circular E field. This, here we have like a moving magnet causing a circular E field. Here we have moving electric charges causing a circular B field. Okay. All right, pretty cool. Now that's not the last word on electricity and magnetism, but it's the last word for now, because I want to talk about an entirely different subject for a little while, and then come back to electricity and magnetism and make the connection between the two subjects. Ben.
This is sort of off subject, but,
Yeah, it's okay.
could electricity melt brass or a type of metal?
Oh, yeah. If you, yeah, that's one of the things I was going to tell you about later. Actually, right after, the decade after Faraday discovered this, there was another English physicist, a guy named Joule, who studied the heating effects of electricity. And he actually discovered that the heat generated by current going through a wire is actually proportional to I squared times the resistance. So, he did a bunch of experiments that actually measured the heat when you put electricity through a wire. And if there's enough current, you can melt things. For example, the first time this was noticed was when people saw examples of where lightning hit metal objects. There was one case I remember reading about where a guy had like a crate of silverware, and that he was storing in a shed or something. Lightning hit the shed and just hit the crate. It created so much heat that it melted the silverware together. So you certainly, people knew that a lot of heat could be generated if you had enough electricity.
If Would that mean how you're telling us that the Earth's magnetic field is going to switch?
Oh, yeah.
Is that going to create a circulating electric field that's really big?
Oh, because of the change in the magnetic field. Well, actually, I doubt it would cause a really big one because that change probably takes place. Let me see. On average, I think the Earth's magnetic pole reverses every.
50,000
Was it 50? I was thinking of even bigger term. It was like a couple of 100,000 years or something. And I think from what scientists have been able to figure out, it takes a couple of thousand years to shift. So if you slow that change down, if it's something that happens really gradually over a couple of thousand years, then this change in magnetic flux never gets very big. So, yeah.
Wouldn't it also if lightning hits sand, then it would.
Oh, we confuse it together. Yeah.
Which would make flash or something like that?
Yeah. Right. Right. Troy.
What you were saying about when the lightning melted the silverware,
Yeah.
is that the same one when silverware became magnetized?
Yeah. Some of it also became magnetized. Exactly. That's the same story. Okay. So I'm. Like I say, I'm not done with electricity and magnetism yet. We have one more brilliant guy to cover, whose name is James Clerk Maxwell. But in order to set up what he discovered, I need to tell you first about some things about light. So, major shift of topic here. So let's shift markers along with topics. And spend a week or two now talking about light. Yeah. And probably won't finish. Yeah, right. So it'll be after Christmas vacation that I finish telling you these things about light. But we'll get started now. And the first thing I have to do is review some things that Newton discovered. One thing in particular. So let's review Newton's theory of colors. And those of you who weren't here last year, this isn't review for you, but it's easy enough. You'll understand it. Those of you who were here last year will remember that when Newton was 23 years old and living on a sheep farm, one of the things that he decided to do was darken his room, board up the windows, let light come through a little tiny hole. Okay, so the sunlight comes through only a small hole, and he puts a prism on the other side of the hole that the sunlight has to pass through then. And this wedged piece of glass causes the light to bend. Okay, that's refraction. All of us are familiar with that. Anytime you send light through at an angle through a piece of glass, it bends it, right? And you can see this in light going through water. That's why a straight stick looks bent in water, right? Because the light is bending when it goes from the water up to the air. Okay, so Newton knows that if he passes the sunlight through this wedge of glass, it's going to bend that light. And then he lets the light go across the room and be displayed on the far wall. Now, who remembers what he sees? Evan.
He sees the different colors spread out.
Spread out, right. He doesn't see just, I mean, he's got this narrow beam of white light going into his prism. What he sees over here is a... Yeah, exactly. He sees a whole spectrum of colors. That is elongated, spread out, and goes from, who remembers, what color does he see down here at the bottom? Troy.
Blue? Or
You had a 50-50 chance, too.
okay. Push the button.
Oh, I see. Oh, that's clever. Red, and then up top, say violet. So, I mean, he's got, and then you got blue, green, yellow, orange. No more white light at all. All this white light that came in this narrow beam has been now spread out, and you can just see all these colors. Okay, so that's what Newton saw. And does anybody remember you get major points if anybody remembers roughly the year that Newton did this experiment? 18.
1620?
1680 is not bad. 1620s, that was 20 years before he was born, so he was way ahead of schedule.
1660.
Okay. 1666.
I was close. I was pretty close. I was almost
Yeah.
Yeah, it's not that much.
Okay. Now, Newton didn't publish. I mean, I remember telling you the story last year about how when he first published this theory, gave a paper on it to the Royal Society there in London.
Not Robert Hooke.
Yeah.
Robert
Hooke.
okay.
Hooke considered himself the great expert on light in all the world, and so he didn't like this young kid, telling him that he knew more about light than the great Hooke. So Newton got all kinds of opposition, and he got pretty mad at Hooke, and he just decided, to heck with it. He had a whole bunch of other discoveries he had made in optics. He said, okay, you don't want to listen to what I have to say, that's fine. I don't have to tell you. And so he didn't publish this work, his book on optics, for a long time, until Hooke finally died. And as soon as Hooke died, then he published his book. So the book actually didn't come out until, this was when the experiment was done. I'm going crazy here. Let's do red. And book published in 1704. Coincidentally, less than a year after Hooke died. Selah.
Didn't Hook sometimes make up stuff?
Well, yeah, I mean, Hooke actually was a smart guy, and he did make some legitimate discoveries. I told you about at least one of them with his law of springs. He was a clever guy. His weakness was that it was crucial to his whole self-image that he be known as the greatest physicist in the world. So he took credit for everybody else's discoveries. So he was very obnoxious that way. So, yeah.
So was light his main discoveries?
No, he did work in a lot of different fields, actually. He did work in light. He actually even did work in biology. He made some discoveries with microscopes. He did work in mechanics. He designed certain instruments and did that spring law that I told you about. So there were. He did some work on strength of materials. So I mean, he was a smart guy. It's just that it is obnoxious to. He took credit for every one of Newton's discoveries, basically. So that gets old after a while. Selah.
I remember in my old school he did something about cells. He like drew a picture. Did he actually do that, or did he steal that?
Oh, no, I think he actually did that. He did work on in the 1660s, the early 1660s. He was doing work with microscopes. So I think he actually, yeah. Okay, now Newton made not only this discovery about light, but several others that I told you about last year, and even a few that I didn't tell you about. And all those discoveries were in this book that he published in 1704. Now, there really wasn't much else discovered about light for a long time. Basically, this book of Newton summed up what people knew about light almost for the next 100 years. And then suddenly, around 1800, there were 3 major new discoveries. And I want to tell you about those 3. But yes, Troy.
Which of Newton's books were published first? Was it the Principia or the?
Yeah, Principia came out. This is a year that everybody should know. This was the book that paved the way for the whole scientific era and completely, radically changed every single one of your lives. So you should have this ingrained in your memory. You should worship Newton for having published this book and have ingrained in your memory the year it came out.
Is it that optics book?
Is it an obvious book?
Optics.
No, this is the optics book. This is his book on the laws of motion and gravitation, and everything he explained with those laws came out in 1687. That's, yeah. Okay. It's actually helpful to, I mean, one of the reasons that I give you these dates in class is because it's when you're learning all this history of science in this class, and you should be trying to put that together with what you're learning in your history class, too. I mean, you learn mainly political history, of course, in your history class, but these dates shouldn't be blanks to you. You should be able to call up other things that you know that were happening around that time, and start getting a feel for what these periods were like. Selah.
The book in 1687 has something to do with rainbows.
Oh, no, he covers rainbows in the 1704, the book on light, which is called Optics. This one, is usually, this book, the first book Newton published, is called the Principia, and that is short for, the full title of the book is Mathematical Principles of Natural Philosophy. They called science natural philosophy back then. Okay,
My
so,
brain fell asleep, so I don't know.
hmm?
I think my brain has fallen asleep. I don't remember that.
Oh, okay. Well, you remember about gravitation and stuff, right? So, yeah, the apple and the moon and all that. Okay, that was in this book. Okay, now, so anyway, I was telling you that for a long time after Newton published his book on optics, nothing much happened in the field of optics. And then, suddenly, three things happened really quickly. So,
All done by one man or
nope,
separate?
three different guys. So let's talk about, let me see, three discoveries about light that all happened right around 1800. And the first one was made by a guy whom you have heard of.
Gilby? No, Hans Christian.
William Herschel. Now, Troy's drawing a blank.
Herschel. Oh yeah. Well,
Do you remember? I mean, I didn't stress this.
Hershey's candy,
Hmm?
That's what I remember. His last name reminded me of Hershey's candy.
Yeah. Okay. Well, that's not the most important thing about him. He was an astronomer, and I remember telling you about him when we were talking about telescopes. And I told you that, you remember Galileo's first telescopes magnified by a factor of like 20 or 30? Well, Herschel built these huge telescopes. Yeah.
And I think he discovered Neptune.
Yeah, exactly. Exactly. It was Uranus. Yeah, and he so he made many discoveries in astronomy because he was the first to build these incredible telescopes that gathered enormous amounts of light, magnified by factors of thousands. I mean, his most powerful telescope, I believe, magnified by a factor of 6,000. So, I mean, he was a great astronomer. But, yeah, Troy.
Was it the American?
Um,
I think of someone else.
no, he was English. There still isn't too much science going on in America right now. Most of it's still going on in England and France. Now, Herschel, so Herschel was mainly an astronomer, and he built these huge telescopes, gathered all this enormous light. One of the objects he was interested in studying was the sun. But, of course, if he points his big telescope at the sun and looks into it, he's in trouble, right? So what does he have to do? Well, now I'm not going to take questions because I want to get just a couple of things out before I. Let me get something out before you ask questions. So Herschel decides, well, what he has to do is take a piece of glass that is darkened, and he used different color glass in front of his telescopes to block the light, and so the image was dim enough so that he could actually look at it. Now, one of the glasses that he used was, if you looked at the sun through this glass, it blocked enough of the light so that he could look at it, and the sun looked red through this glass. Okay, so he had a red glass, basically, a red stained glass. Now, but he found that there was a problem. Even though the light wasn't too bright to look at, his eyeball would heat up basically, when he looked at this red image of the sun. Okay, but it didn't happen when he used a blue glass. When he made the sun look blue, he could and dim, he could look at it, and his eye wouldn't get hot and uncomfortable. And so that gave him an idea. Sayla, what
You
you're?
have a laser, didn't you?
No, you're about 155 years off. The laser was in the 1950s. That's a much more advanced development. But he has stumbled on something really important here.
Maybe sunglasses.
No, not sunglasses. He's not going to invent sunglasses. Troy, you got it?
Finds that like lights a type of electricity. Or kind
No. See, I haven't told you enough. I mean, you're all guessing at the answer here. I haven't really even gotten to the question. But it's going to have to wait until next time. But I'll continue on Herschel next time. He has stumbled on something really important.